possibilities. So these lectures are going to be given by, you have to accept the recording there, Florian?
Sure.
Are going to be given by two speakers, actually. So Professor Bernard Carr, who is connected from London. He's a professor at Queen's Mary University College of London. And then Florian here from Munich, whom you met already. And they're going to share the presentation, and they have organized everything for us. So please, Bernard, now you can share. And we should be able to see. Yes, that's perfect.
So can you see my screen?
Yeah.
Great.
Looks good.
Tell me when to start.
When you're ready, now. Go ahead.
Okay, well, I am Bernard Carr, and I'm very sorry I cannot be with you in person. I am currently in London, but I'm delighted that my friend and collaborator Florian KUHNEL will be able to give the lectures with me, and he is there in person. So here is the title of the talk, Primordial Black Holes as Dark Matter Candidates. And although we will primarily be focusing on their possible role as dark matter, we will also be talking about the subject more generally to put it into context. So my first slide is very nostalgic, because my first meeting, the first conference I ever attended as a PhD student, was in 1972 in Les Houches, and it was on the topic of black holes. And that's, in fact, it was the first big conference on black holes that really ever took place, almost exactly 50 years ago. And that's why I was actually particularly looking forward to being there in person, but obviously the pandemic has made that impossible. But I hope that this conference, this school is just as enjoyable and historic as the school I attended in 1972. The other thing I should point out is that although I've been working on primordial black holes for about 50 years, it was a rather subdued topic for the first 3 or 4 decades with very few publications. And it's only in the last 10 years or so that the subject has really become so popular. I'm showing here the number of papers on primordial black holes, either refereed or non-refereed, ever since 1974, which was when I first wrote a paper on the topic. And you can see it was always below about 30 or 40 until around 2000, and then the subject picked up. And then in the last few years, actually since primarily since the LIGO event, it's really soared. So now we're having something like 500 papers a year on the topic. And so this is the most recent period going up to the current year. And I have to say that from my perspective, in a way this is good news, because it means people are taking the subject very seriously and think primordial black holes really are important. On the other hand, in a way it's bad news, because I often have to talk about the subject and I have to try and keep up with the literature, and I find it almost impossible now to read all the papers. So in a funny way, I preferred it when not many people believed in primordial black holes. However, I hope by the end of the lectures you will be among the believers, or at least people who think this is worth studying. I should also say, on a purely personal note, that actually it's somewhat ironic, because the first 2 papers I ever wrote when I began my PhD were on primordial black holes. The first one was with Hawking in 1974, and the second one was my own paper in 1975. And these are actually my most cited papers. 863 and 792. And in a way, that's rather bad news. Of course, I'm pleased that they're highly cited. On the other hand, it in some sense means that my career has been downhill from the start, in the sense that none of my later papers were cited as much as this. And so, since I think most of you are new PhD students, bear in mind whether you want your first papers to be the most cited or not. However, I can end this on a somewhat more positive note by saying that actually the paper I wrote with Florian in 2016 is also been highly cited. And so I think I can say, and that was also on primordial black holes, and so I think I can say my career has had a resurgence towards the end. And I should say I did formally retire a few years ago, although I'm still research active. Now, the plan of the lectures, we have 2 lectures. I'm going to give an overview of black holes, and with quite a lot of emphasis on history, because that's something people don't often hear about, even if they're active researchers in the field. And then Florian is going to talk about the formation, the evaporation of black holes, and to some extent about the constraints on primordial black holes. We probably won't finish that topic in the first lecture. So in the second lecture, we'll carry on talking about the constraints. I will then talk a little bit about giving an introduction to PBHs in the context of dark matter, which of course is the topic relevant to this pool. And then Florian will take over and he'll talk about the numerous conundra, observational conundra, which could in principle be explained by primordial black holes. Because I have to say that we still don't know for sure that primordial black holes make up the dark matter, obviously. And obviously you're mainly hearing in this school about the particle dark matter candidates. But there are tantalizingly many observational conundra which could in principle be explained by primordial black holes. And we're going to spend most of the second lecture talking about that. And we're also going to talk about the possibility that there could be rather massive primordial black holes, or even what are called slabs, these stupendously large black holes. And these black holes, they couldn't make up the dark matter, their density is too low, but they still are, of course, dark. And then finally, Florian is going to talk about the possibility that the dark matter could be some mixture of primordial black holes and WIMPs. And in some sense, I think that would be popular maybe with the students at this school, because you're mainly learning, of course, about the WIMPs, the particle dark matter, and we'll end up with some general conclusions. So those are the general plan for the lectures, but we don't quite know how long we're going to have to get through, because it depends how many questions you ask and things like that. But that's the tentative plan. So let me start off with my overview and historical introduction. Incidentally, I should say we have provided lecture notes, which I think you had time to look at over the weekend. Those lecture notes, to some extent, were based upon a recent review myself and Florian have written about primordial black holes as dark matter. But that review is much longer than this. This is a sort of brief. The notes we've given out are a shortened version of that, and also with quite a lot of extra material as well. But the key point is that all the references you'll need are in the review, and we won't be citing all the references in these talks. Now, I want to first of all put black holes into context by talking about non-primordial black holes. And as I'm sure you know, there is overwhelming evidence now for different types of black holes. In particular, they're stellar black holes, the black holes which form as a result of stellar collapse, and the mass range 1 to 100 solar masses. We know that, for example, that we've known ever since the 70s that there are a lot of X-ray binaries where one of the components must be a black hole, and the best example of that is Cygnus X1. Most recently, of course, we know that LIGO detected gravitational waves from the merger of coalescing black holes, and those black holes were presumably, well, they were at least in the mass range between 10 and 100 solar masses, not necessarily of stellar origin, as we'll see, but the mainstream view is that they are of stellar origin. But I would say there's also overwhelming evidence for supermassive black holes in galactic nuclei, not necessarily active galactic nuclei. That AGN stands for active galactic nuclei, but in particular in AGN as well. And they have a mass range between about 10 to the 6th and 10 to the 11th solar masses, so really huge. Our Milky Way has a 4 million solar mass black hole. Typical quasars are powered by a 100 million solar mass black hole. The biggest black hole we're aware of in a galactic nuclei is called TUN, and that is 70 billion solar masses, so really huge. And what's interesting is that we now think that all galaxies have got black holes in the center, and the mass of the black hole is more or less proportional to the stellar mass. So it might be a bit hard to resolve. This is plotting the mass of the black hole against the mass of the galaxy, and it lies on a nice straight line. So there's the straight line, it goes all the way from our own Milky Way all the way up to this object TUN. Now, there are also possibly intermediate mass black holes. They're in the mass range 1,000 to 100,000 solar masses. The evidence for this is not quite as strong, but personally I think it's likely. There are, for example, ultraluminous X-ray sources, and here's one which is thought to have a 500 solar mass black hole powering it. The ultraluminous X-ray source is not in the middle this time, it's in the outskirts of the galaxy. And it's thought that some globular clusters could have intermediate mass black holes in the middle. Here is one called Omega Cen. And actually there's good evidence that even the first stars to form, so-called population 3, might have been in the intermediate mass object. Now, and I've just borrowed a slide here from Roger Blanford at the recent Penrose Symposium, which just makes it clear that black holes are now famous, if you like, that these are the three, I won't go through the names. Of course, in 2017, of course, the Nobel Prize was awarded for the detection of LIGO gravitational waves. And then, of course, we had just this last year, we had the award of a Nobel Prize for the study of the evidence for the black hole at the center of the Milky Way. And also, of course, you will all have heard of the M87, which was actually imaged by the Event Horizon telescope. By the way, there is an artist's impression of TUN 618, which is the biggest one I mentioned before. So that's just to persuade you that black holes definitely do exist. But now primordial black holes are a different beast. And the first thing I need to point out is that the size of a black hole is its Schwarzschild radius, and that's just proportional to its mass. I'm sure you know that. But what that means is the density a region has to attain in order to collapse goes like 1 over m squared. So for something like the sun, it's somewhat bigger than nuclear density, but if you have a very large black hole like that in a galactic nucleus, this density is very low. It might just be the density of water, for example. But now, what can you therefore get black holes which are smaller? If you want a small black hole, the crucial point is that you need a very high density. But of course, you will have heard how in the early universe, the density can become arbitrarily high. I know Anne Green talked about this, and roughly speaking, I'm here assuming the Big Bang model, and in the Big Bang model, the cosmological density just goes like 1 over gt squared, where t is the time since the Big Bang. So the density becomes arbitrarily high. So simply comparing this cosmological density with this density required to form a black hole tells you that the mass of the black hole must be essentially CQT over G. So it's proportional of the time. That is technically what we call the horizon mass. In the Big Bang picture, light travels by a time t, light has travelled a time c times t, c is the speed of light, and the mass within that distance is called the horizon mass, and it's CQT over G. Now, the earliest time at which you can apply this model is the Planck time, 10 to the minus 43 seconds, before that classical relativity breaks down, so that corresponds to the Planck mass, 10 to the minus 5 grams. On the other hand, if you go to the Qcd Phase Transition, which is at 10 to the minus 5 seconds, the mass is 1 solar mass. At a time 10 to the minus 23 seconds, that's when the horizon size is basically the size of a proton. The mass of the black hole forming will be 10 to the 15 grams, and we'll see in a moment why that's important. Now, of course, it's interesting to ask how big a black hole can be. It used to be said that it was unlikely that primordial black holes would form after 1 second, because after that you might mess up nuclear synthesis, and that would give an upper limit of about 100,000 solar masses. I no longer believe that argument. In fact, we're going to talk about the possibility that primordial black holes could be even bigger than that. But the main point is that primordial black holes can span a huge mass range, all the way from the Planck mass, which is more like an elementary particle, to astrophysical masses, the sort of masses you see for black holes in galactic nuclei.
Question here? Sorry?
Is that a question?
Yes, thank you. Just a general question. So is the idea here that we have primordial black holes forming in the very early universe, and then there is a break in time, and then the black holes that, like standard black holes, form later?
Yes, I mean, but this is a general argument which says that in principle, the universe can be dense enough to form primordial black holes of mass all the way down to the Planck mass. But it's important to stress that this doesn't mean they don't necessarily form. That's a necessary condition, but not a sufficient condition for forming primordial black holes. And in order to form black holes, you have to have particular mechanisms. And this is what Florian is going to talk about later on in this lecture. But also bear in mind, I'm going to explain that only a tiny fraction of the universe goes into the black holes. So when you form the black holes, it doesn't at that time make an enormous difference to the cosmological evolution.
Okay.
Is that okay?
Yes, and then just a quick follow-up. So at what point in cosmological history do non-primordial black holes begin forming?
Oh, well, the black holes I was talking about before were all forming at very late times, that's to say, after galaxy formation. And galaxy formation is thought to occur at about 1 billion years after the first galaxies would form at about 1 billion years, which of course is far, far later than that, this.
Okay, great. Thank you.
Okay. So now, let's carry on. I would say one of the first papers, and in a sense the first paper to talk about primordial black holes was by Stephen Hawking, he was my PhD supervisor, and he was interested in the Planck mass black holes, the smallest ones to form, and he had the idea that these would be charged and that they would capture electrons. If they were positively charged, they would capture electrons. If they were negatively charged, they would capture protons. So they could then form neutral atoms. And he was interested in the idea these neutron atoms would have certain signatures. They could be captured in bubble chambers, and you would see distinctive tracks. They could also get captured by stars. For example, you could get these black holes being captured by our sun, and you'd get an accumulation of them. And it was even thought that might explain the solar neutrino problem, which was then unexplained, the fact that there seemed to be too few neutrinos coming from the sun. And he was also interested in the possibility that neutron stars would capture these black holes, and then the black hole inside the neutron star might eventually swallow the neutron star. That's an idea which is still actually quite topical. Now, in the end, this picture didn't work because it turned out that due to quantum effects, these black holes are not expected to be charged. They lose charge through basically a Schwinger type effect. And so this specific scenario probably doesn't make sense, but nevertheless it was the first scenario which actively proposed that primordial black holes could form and have interesting consequences. Now actually there was a snag, and that was that some years earlier, in 1966, Zeldovich and Novikov had actually considered this possibility and decided that it was impossible because it would mean that the black holes would accrete, because of very high density, the black holes would accrete very, very fast. And in fact, they predicted they would grow as fast as the visible universe, and they would be, well, at least until the end of the radiation era. So they predicted that all black holes, primordial black holes, would grow to about 10 to the power 17 solar masses. And that's in conflict with the observation. So they basically said there can't be any primordial black holes. So although this might be said to be the first paper on primordial black holes, it was also actually put a stop to the field for quite a long time. I got a slide giving the argument, but this may be too technical, so I don't think I'm going to go through this in great detail, but just for the people who are used to this, the idea is that they applied what's called Bondi Accretion. If you have a black hole, I hope, can people see my little arrowhead, my mouse head? I think they can. Yeah. If you have a black hole, the matter within a certain radius, the so-called accretion radius, is swallowed up, and it depends upon the sound speed, which depends upon the pressure. And this is called the Bondi Accretion formula, and you can predict on the basis of that, using the density of the background cosmology, which is well known. K is the equation of state, so P is K rho. You can predict how fast the black hole grows. And if you integrate that, you get a very simple formula for the mass growth. And T, I'm missing out some factors here, but T is essentially the horizon mass. And this quantity Bt is the horizon mass at time t. And what you can see is that if the black hole is initially much smaller than the horizon mass, you can see that it doesn't grow at all. On the other hand, if the black hole has the same mass as the horizon, then it grows at the same rate as the horizon. So if this argument is too technical for you, I mean, because I know most of you aren't astrophysicists, don't worry about it. The important qualitative point is that it predicts that black holes grow as fast as the universe. But sub-horizon ones don't. But there was a problem with this, because this actually neglected the cosmological expansion. First of all, it's a Newtonian argument. It isn't a relativistic argument, and it neglects the cosmological expansion. Now, when I became Stephen's PhD student, the first paper I wrote was actually disproving this argument. And the reason was we looked for a relativistic solution in which the black hole grows as fast as the horizon. Well, technically it's called a cell-similar solution. And we found that there was no such solution. In other words, we showed that no black hole which was formed locally could possibly grow as fast as the horizon. And this disproved the Zeldovich-Novikov conclusion. And furthermore, since it doesn't grow as fast as the horizon, it soon falls below the horizon size, and that means from the Zeldovich argument, it doesn't grow very much at all. So I'll just go back to this. Once you're in the regime that it's much smaller, then you don't get much growth at all. And I should say, the point about the Zeldovich-Novikov argument is that you did expect the black hole to have a mass comparable to the horizon when it forms. I have a slide on the technicalities of this proof, but I'm not going to go into it now. I'm just going to go straight through it. But the point about this paper was that it showed there was actually no observational evidence against them, because there was no reason to show they would all grow enormously. So let me just, I'm going to miss the next, oh, right, that was just a picture of me. Oh, you can't see me now anyway, where I was, that's in the old days when I had a beard. So that picture was taken, nearly 50 years ago. That was when we were at Caltech, 1974. Now, I'm going to miss out the next slide. It's too technical. But in 1974, which was the year I was with Stephen at Caltech, Stephen discovered one of the most important results in theoretical physics, I would say, of the last 50 years. He discovered that black holes aren't black after all. They emit particles like a black body with a thermal spectrum. So black holes have a temperature, and this temperature is inversely proportional to the mass. So it's very low for a solar mass black hole. It's about 1/millionth of a degree, but it could be important for black holes which were much less than a solar mass, i.e. for primordial black holes. So this is just the abstract from Stephen's paper. That I don't want you to read it now. I just want to show this for historical reasons. This is I'm assuming people know what the space-time diagram looks like for a black hole, but this shows the black hole forming a singularity. The event horizon is there like a cylinder, but because of the emission of radiation, the event horizon shrinks and the singularity eventually disappears, and you get left with the black hole radiation. I want to stress this was such an important result. This is the temperature for the black hole, about 10 millionth of a degree for a solar mass. There is Stephen. why this is important is because it unified for the first time quantum mechanics, general relativity, and thermodynamics. And that's what makes a theory so great, when it unifies previously distinct areas of physics. When Stephen discovered this, I was speaking to John Wheeler, who actually coined the word black holes, and he once said to me that talking about this result, it was such a beautiful result that just talking about it was like rolling candy on the tongue, which I always thought was a lovely phrase. I have to say there's still no definite evidence for primordial black hole evaporation, quantum emission, but it's such a beautiful result that normally almost everybody expects it to be true. But the point I want to stress is that Stephen was only led to the result because he was thinking about primordial black holes, because only primordial black holes could be small enough for this effect to be important. So even if primordial black holes don't exist, it's been very important to think about them. And I think that's an important lesson for physics. Sometimes it's important to think about things even if they turn out not to be true. For example, you might think about something like M theory. Even if M theory isn't right, I bet you that having thought about it will be important. But obviously it's much more interesting if primordial black holes did form, and that's what I want to focus on, and myself and Florian want to focus on for the rest of this lecture. Now, let's go into Pbh evaporation in a little bit more detail. The temperature of a black hole, as I said, it goes like 1 over the mass, but that means it's emitting thermally. That means it evaporates completely. The emission rate goes like T to the 4th, m to the minus 4, but the area of the black hole is m squared, so that's, you have an emission rate that goes like 1 over m squared, and it's quite easy to see from that it evaporates on a time scale that goes like m cubed. And which is, for the sun, that's enormous. But you notice that if the mass was about 10 to the 15 grams, the evaporation time is about the age of the universe. The age of the universe is 14 billion years, 10 to the 10th years roughly. And so you can see that 10 to the 15 grams, this magic mass which I emphasized in an earlier slide, corresponds to the black holes which are evaporating today. So that's about the mass of a mountain, but the size is just about the size of a proton. But what's interesting about these black holes is that they're evaporating today, and the final stage of their evaporation is an explosion. And the mass goes, because the mass goes like 1 over m, as the mass gets smaller and smaller, the temperature goes up. So the evaporation terminates in an explosion. So, and a lot of people have been interested. I think Jim Klein is there, and he's someone who's been interested in these explosions. But most of the life of this black hole, it's emitting gamma rays. It's got a temperature of about 10 to the 12th degrees, 100 MeV gamma rays, but in its final phase it explodes, and it releases something like 10 to the 30 ergs. So it's fairly dramatic if this was seen. However, unfortunately, this was bad news, because in the sense that even in 1974, when Stephen discovered black hole radiation, one was able to look at the gamma ray background at 100 MeV. And the density at 100 MeV of the gamma ray, the extragalactic gamma ray background, already told us that the density of the black holes of 10 to the 15 grams, in units of the critical density, this is called omega. The critical density is the density of the universe, which just expands forever. That had to be less than about 10 to the minus 8. And that meant it would be unlikely that you could actually detect the explosions. I mean, obviously we were very excited into the possibility that you could detect one of these objects exploding. If it exploded, you would have evidence first for primordial black holes, and secondly for the Hawking radiation. But unfortunately, this gamma ray limit made it rather unlikely that we would detect them.
Question?
At least with the standard
Quick
modern
question,
particle.
sorry.
Sorry, a question?
Yes, thank you. Could you say a little bit more about why these explosions are happening? What processes lead to them?
Well, okay, let me go on to the next line. It is possible, although I'm saying that's the standard view, some people have suggested that some of the short gamma ray bursts could be black hole explosions. This was the suggestion of David Klein. This is distinct from Jim Klein, but David Klein suggested that some of the short gamma ray bursts could actually be due to primordial black hole explosions. Now, I must stress that most gamma ray bursts are not due to primordial black hole explosions. They're known to be at cosmological distances. They could be associated with big black holes. However, these primordial black hole explosions would be very local because they're all within our galaxy, so they're not cosmological. Because remember, these black holes, they're very low mass, so you wouldn't see them at a cosmological distance. But they're very numerous, of course. They might be very numerous, so they could be quite close by. They could just be, a distance of the edge of the solar system or something. So now I'm not quite sure specifically what you were going to ask me. Are you asking me why they explode or how we would observe them as explosions?
I am asking why they explode.
Why they explode?
Yes.
Well, because the temperature goes up as the mass goes down, they get hotter, and therefore they emit more rapidly. Most of their lifetime, they have the mass, their initial mass of 10 to the 15 grams, and that's when they're sizzling away producing gamma rays. But when they finally finish their evaporation, of course, their mass goes down, so they're going to get hotter and hotter and hotter. And eventually you get to a stage when it loses all its mass, remaining mass, in about 1 second. And that happens when it gets down to about 10 to the 10 grams. So in other words, calling it an explosion is just a way of saying, the last evaporation phase is very rapid. And when I say you lose 10 to the 30 ergs, that corresponds actually, I think, to 10 to the 10 grams, not 10 to the 15 grams. So it only goes explosive in the sense when it gets down to a mass well below 10 to the 15 grams. But and when that mass is depends precisely on your model of particle physics. But if, for example, you have to wait till you get to 10 to the 10th grams, then it would correspond to something like 10 to the 30 ergs. And it would all go in about a second. You can have other models. For example, you can have if something funny happens at the Qcd epoch, you might even have explosions occurring at a much bigger mass, 10 to the 13 solar masses, for example. And people like Klein, who want to have them detectable, they have to say that something funny happens when you get to the Qcd epoch. So I hope that's clarified that. But one other point I want to make is that if the black hole is too large, if it's bigger than 10 to the 26 grams, which is the mass of the Earth, then the temperature would be less than the temperature of the CMB, the microwave background, the cosmic microwave background, which is 3 degrees. And so those black holes wouldn't evaporate after all, because the accretion would dominate the evaporation. And so I adopt a terminology of calling black holes smaller than 10 to the 26 grams, the mass of the Earth. I call those quantum black holes because they are the ones for which Hawking radiation is important.
Excuse me?
Not everybody uses that terminology, but that's how I use it. So
Excuse me, sorry. Can I ask a question?
Sorry, a question?
Just a small question. Is there any proof or any calculation to prove that there is a final explosion in the last times of the black hole? Or because we know from computation that, okay, there is Hawking radiation, so it evaporates, it gets smaller with time, but what happens at the last stages, I think that the computations for that are not solid, I would say.
Well, yes.
Because you have like non-perturbative effects at the end, and yeah.
There is uncertainty there. Sorry, is that question coming from a student or from one of the people who's an expert on the topic? So I can...
Yes, just a student.
It's fine, that's great. Well, because I know Jim Klein is there, you see, so I wanted to make sure you weren't Jim. The point is that the detectability of the black hole explosion depends on how many there are. And that depends on this parameter omega Pbh, the density of the black holes. If that is low, they'll be so far apart that you won't detect them anyway. Now, we know from the gamma ray background we have this constraint of 10 to the minus 8 on the density. And that tells you where the nearest one is going to be. In other words, it tells you how often they can explode. Well, I'm assuming now they're clumped inside galactic halos. So the first uncertainty is how many there are. This is merely an upper limit. But the second uncertainty involves the actual nature of the evaporation itself. And there are two sorts of uncertainties. One is to do with the particle physics picture. Does something finally happen at the QCD stage, for example, in which case you might get an explosion even before you get down to 10 to the 10th grams. But then there's a more fundamental question of whether we actually believe the Hawking result itself down to these very low masses. I mean, we know the Hawking formula must break down when you get down to the Planck mass, but some people have argued that it also breaks down before that. And I will stress again that we still don't have any direct evidence for Hawking radiation. So there are elements of uncertainty. So I'm just presenting the sort of, the most plausible picture as it's currently understood. Now let me carry on. I just want to point out that primordial black holes, because of their huge range of masses, have a huge range of interesting consequences. The ones which have got the Planck mass, they're in the quantum gravity regime, and there could be all sorts of things. They could, in principle, Hawking radiation might stop and they might generate Planck mass relics, but there could also be extra dimensions when you get to this scale, because these are very small black holes. You could have higher dimensional black holes. We're not going to talk too much about that. The black holes less than 10 to the 15 grams, these are the ones that have already evaporated. So these aren't going to be very relevant to the dark matter problem. However, they are important in the sense that they could have consequences for the early universe. They could affect Big Bang nucleosynthesis. They could reionize the universe and things like that. And so we're not going to talk about this too much because it's not relevant to dark matter. But there's been a huge amount of literature on these topics, because these black holes, smaller than 10 to the 15 grams, although they don't exist now, they could have had observable consequences, and you thereby get interesting constraints on the early universe. As I mentioned, the ones at 10 to the 15 grams, they're evaporating today. They could contribute not only gamma ray bursts, they could contribute to the extragalactic and galactic gamma rays and cosmic rays and things like that. So if you were able to detect these black hole explosions, it would give you unique information about high energy physics. And so we'll say a little bit about that, but not very much. We're mainly going to be interested in the ones which are bigger than 10 to the 15 grams, and they have all sorts of gravitational consequences. Obviously, they could provide the dark matter, which is the main focus of our lectures. They could also be a probe of what are called critical phenomena. You'll hear more about those from Florian. They could have all sorts of dynamical and lensing effects. They could generate gravitational waves. They could be important because of the big black holes in galactic nuclei. So that's just a slide to talk about the huge range of consequences primordial black holes could have. And of course, the ones we know definitely exist, they're all bigger than a solar mass. So this is another range. Now, obviously, I should say a little bit about dark matter, although we'll be talking about this much later. Myself and Florian are going to try and persuade you that primordial black holes could be the dark matter, although I realize this may not be the most popular conclusion among the people at the school, because most of the time you're talking about particle dark matter. However, let me just give you, what are the reasons? The first reason is that we know black holes exist. I hope I persuaded you of that right at the start. So you don't need any new physics. I mean, the particle dark matter may exist, but it does require some new physics which goes beyond current observations. And I suppose the reason most people have got interested in this subject is because of the LIGO results, because as we'll see, LIGO black holes could conceivably be primordial. I would say the main argument against primordial black holes, which I'll come to later, is that it does require very fine tuning of the collapse fraction. Only a small fraction, at most a billionth of the universe, can have collapsed the primordial black holes, even if you want to explain all the dark matter. So the question is, why is it so small? If you have too much, you're going to vastly far too much of the universe in black holes. I think this picture, I like this picture because I found it outside a French restaurant for some reason or something. So I wanted to introduce a French element. But the other point to make is that in some sense, all black holes are dark, but normal black holes, which form at late times, stellar and supermassive black holes, could not provide the dark matter. And the reason for that is as follows. Big Bang nucleosynthesis tells us that the baryonic density is about 5% in units of the critical density. So this is a plot of the light element abundances against the baryon to photon ratio. And this is to say the production of helium, deuterium, and lithium. And one of the great triumphs, I'm sure Anne Green explained this, one of the great triumphs of the Big Bang is that it can explain the light element abundances, which were formed at about 100 seconds. But that only works if the baryonic density is about 0.05. And all the black holes which we know exist, stellar and supermassive black holes, have to form from baryons. Now, by contrast, the visible material, like stars, is about 1%, and the dark matter density is about 0.25, 25% of the critical density. And so that's very important. That tells us we need both baryonic dark matter, which is sometimes called machos. Actually, it's probably just intergalactic gas. But we also need non-baryonic dark matter, and that, of course, could be WIMPs. That will be the view you mainly heard about. So that's because 0.05, the baryonic density, is only a fifth of 0.25, the dark matter density. The dark matter associated with halos and clusters and things like that. This is distinct from the dark energy, which is the 0.7 or something. So in some sense, primordial black holes are non-baryonic. They're forming before nucleosynthesis, Big Bang nucleosynthesis, which is why they're not affected by this constraint. And in some sense, they have features of both WIMPs and machos. They're WIMPs in the sense they're non-baryonic, but they're more like machos. Machos stand for massive compact halo objects. But they're more like machos in the sense that they're sort of quite large and astrophysical. But they are non-baryonic. Now, this idea that primordial black holes could provide the dark matter is actually very old. The first paper written on the subject I can find was by George Chaplin in 1975. I put the abstract, don't try and read it, but he pointed out that in principle, if primordial black holes form, they would be dark, they could make up the dark mass, providing, of course, they don't evaporate. I mean, he had this paper about the same time as Hawking radiation, but obviously it has to be after the ones which aren't going to evaporate, but that's fine. And then another important paper was by Peter Metsaros, and he said that if black holes make the dark matter, they're going to be important for galaxy formation. And this is a theme we're going to come on to again in the second lecture. If black holes, primordial black holes, make the dark matter, they're going to have many other consequences for the formation of cosmic structures. But perhaps what's most attracted interest in primordial black holes and certainly caused this huge increase in publications was the LIGO events, or LIGO-Virgo events. I'm sure you've seen this diagram, maybe you haven't actually, but this is just showing the mass on the vertical axis of the black holes detected by LIGO. Remember, these are binary black holes which coalesce and generate gravitational waves. And the point, and now, of course, there are a lot of these. I mean, we're well above. I mean, I think when we did our review, there were 10 of them, and now they're more than 10. But the point about the LIGO black holes is that they're bigger than the black holes which we know exist because of X-ray observations of binaries, for example. And because they're the ones in purple in this lower mass range. So it was a surprise at first that the LIGO black holes were so big. The first ones were about 30 solar masses, and now they go to above 100 solar masses. And at first that went against the stellar model, because the stellar models expected the black holes to be smaller. And this raised the question, this is the famous picture of the LIGO detector, but this raised the question of whether the black holes could actually be of primordial origin. Could the black holes detected by LIGO actually not come from stellar evolution, but be primordial? The reason being that they're too large for normal stars. Now, I have to say the mainstream view remained among the LIGO gravitational wave observers is that probably they are stars. The theorists have had to adopted their model a bit by arguing that the stars can be bigger than expected, but nevertheless, among the Pbh community, there is a lot of interest in whether these black holes are primordial, and we may even be giving arguments that they are primordial, but that will be in the second lecture. Another point I want to make is that the fraction of black holes which collapse has to be tiny. And I'll give the argument for this because it's quite important. If we take the ratio of the Pbh density to the CBR density, cosmic background radiation density today, of course it depends on the density parameter of the black hole, which I'll call omega Pbh. The density parameter of the CBR is about 10 to the minus 4. Now, as you go back in time, the point is that the radiation density goes like 1 over r to the 4th, whereas the black hole density goes like 1 over r cubed, where r is the cosmic scale factor. So the ratio of the black hole to the microwave background density goes down like r. R naught is the current scale factor. And it's quite easy to show it has this form. Omega Pbh is the Pbh density, which even if it's 1, which is close to 1, for example, this is tiny. And I know what r is as a function of time. And also, sorry, there's a mistake here in this slide, I've just realized. If you forget this last term, it looks like time to the power of half. So at 1 second, it's 10 to the minus 18 times omega Pbh. But actually, T is related to the mass, and so this is also goes as m to the minus a half. So there's a mistake in this formula, actually. Can you please delete, imagine deleted this T expression? Okay, this should, I've merged 2 equations into one and made a mistake. So forget about the T. This ratio goes like T to the half, but remember, T is proportional to m, so it goes like m to the half. So the formula should be 10 to the minus 18 omega Pbh times m to the half, no T term. So Florian, maybe later on you can correct that in the slides. So the point is here that the collapsed fraction must be tiny. And that's why I said there's a fine-tuning problem. And more precisely, you can ask, what is the relationship between the fraction of the dark matter in black holes, which we'll call FDM, and the collapse fraction, which we're calling 10 to the minus 9, which we're calling beta. And you can see that, for example, if the dark matter was in solar mass black holes, the collapse fraction will be only 1 in a billion. And so that's why I'm saying it requires enormous fine-tuning to explain why you have the dark matter density, if that is the case. It was only a tiny fraction of the universe which has collapsed. And in fact, you can be a little bit more precise. I can ask, what is the fraction collapsing? And the unevaporated fraction, we know that must be less than the cold dark matter density, which is 0.25. I've already mentioned that the ones at 10 to the 15 grams must be less than 10 to the minus 8 from the gamma ray background observations. The ones which are evaporated, there are all sorts of constraints you can have there. They'll generate radiation, the gamma ray background that affect Big Bang nucleosynthesis. Here is just an old paper from '94 which shows the constraints on omega as a function of m from these effects. And so when I talked about the density constraint, that's just this line that goes like m to the minus a half, but the shaded region here is excluded.
Could I ask a quick question, please?
Yes, of course.
Thank you. Going back 2 slides to the mass plot with the LIGO black holes. So you said those heavier ones could potentially be primordial, but wouldn't they have to form after Big Bang nucleosynthesis?
No, the LIGO mass range goes roughly from 10 to 100 solar masses. and those black holes are forming somewhere between 10 to the minus 5 and 10 to the minus 3 seconds. So it's still before Big Bang nucleosynthesis, because Big Bang nucleosynthesis, well, it depends on the weak freeze out at 1 second. So the LIGO black holes are still forming before nucleosynthesis.
Got it.
But that's
okay.
a good point. Thank you for raising that.
Thank you.
So the point about this diagram, as I said, is that this is showing the constraints. The shaded regions are excluded. Now, later on in the second lecture, we'll be talking about these constraints in more detail, but a lot of the focus has been on these constraints. And so what mass range could you have for primordial black holes? I've now taken this is a slide taken from Profumo. He gave a talk, and in principle, there's a large number of mass ranges in which primordial black holes could be interesting, and he uses the terminology. He calls these grain of salt sizes, noceums, space cow black holes, pyramid black holes, evanescent black holes, and asteroid mass black holes. Now, only the latter two in principle could be the dark mass. In the standard evaporation picture, at least, these lower mass ones would have evaporated, but you could invoke some scenario where they get left after all and don't evaporate. But I just thought I'd show you this diagram with reference to Profumo to show that in principle, of course, you have to have some scenario for forming them, but there are different mass ranges in which primordial black holes can be interesting. They're also, by the way, I must apologize to Florian because my lecture is taking more time than I thought. So I'm sorry about that, Florian, but we'll just obviously readjust the later lectures to allow for it. The other point I want to mention is that black holes could be a probe of higher dimensions. I mentioned the possibility that, you know, when you get down to the Planck scale, you could have extra dimensions. And this is very important for small black holes because of its link to particle physics. In M theory, you have extra dimensions. You have n extra dimensions, which are normally assumed to be compactified. In the standard model, they're compactified on the Planck scale. And that means that quantum gravity effects come in at the normal Planck scale, which is 10 to the 19th GeV or 10 to the minus 5 grams. But there are some scenarios in which you have large extra dimensions. The extra dimensions are wrapped up, but they're much bigger than the Planck scale. And in that case, the effective d-dimensional Planck mass is much less than the normal Planck mass of 10 to the 19th GeV. And that has the very interesting consequence that you have what you call TV quantum gravity. That means your formula for the Schwarzschild radius, the temperature, and the lifetime is changed. And what it means is, in principle, you could generate these small black holes at the Large Hadron Collider. But this only happens if you've got extra dimensions which are large. And I have to say there is no direct evidence for that at the moment. But there was a lot of interest in generating primordial black holes in accelerators, and then they would evaporate and they would shine like Christmas trees. Now, these aren't technically primordial black holes, but if they were detected, it would have, you know, huge consequences for primordial black holes. And I wanted to mention this because I understand most of the audience are particle physicists. And the other thing is there is a certain sense in which the whole universe is a primordial black hole. This is a little bit very speculative. So one view is it has been argued when you collapse to a black hole, this generates a baby universe. And from that perspective, this is very, very speculative. It's not the mainstream view, but in that sense, even our universe could have resulted from the collapse of the black hole. Another idea is that you have what's called brane cosmology. This is one version of M theory in which our physical universe is a slice, a brane, BRNE, in a higher dimensional, 5-dimensional bulk. And in what's called brane cosmology, this brane sort of moves through the 5th dimension. And this model, it's called the 5-dimensional Schwarzschild de Sitter model. And in this model, the universe essentially emerges from a 5-dimensional black hole. Now, again, this is very speculative. Not everybody believes in brane cosmology, but I just want to say there is a sense in which all of our universe is a black hole. And this really leads to my final picture, which is summing up this discussion. This is my favorite diagram. It's called the cosmic Ouroboros, and I don't have time to talk about it in depth, but basically it's the snake which swallows its own tail, and around the snake are all the objects, scales of structure in the universe. I've got the scales of structure indicated around the side, and as you go from the top, you go from the smallest conceivable scale, the Planck scale. The scale increases as you go anti-clockwise until you get to the scale of the universe, roughly 10 to the 30 centimeters. So you've got 60 decades of scale. It's like a clock where the body of the snake is like a ruler. Each minute corresponds to a decade. So at the bottom here we have people, and then as you go to the right, you get bigger things like mountains and planets and stars and the solar system and the galaxy and the universe. As we go to the left, we get smaller things like ants and amoebas and DNA and atoms and nuclei and all sorts of subatomic particles. So we sort of had we had the whole universe at the top and the Planck scale at the top left. And the forces of nature link the microscopic and the macroscopic domains. And I won't go into the details of this. It would be a bit of a detour, but I can talk about that later. So the electric, the weak, and the strong, and the electric, weak, and the gut forces, they sort of link the micro domains to the macro domains in ways which could be discussed, but I won't discuss now. But anyway, this is just my favorite picture because it represents the triumph of physics in coming to understand the whole universe, from the very smallest to the very large scales. But now I want to actually use this diagram to draw together everything I said about black holes. This body of the diagram represents a scale. So I want to take the scale, the size of the black hole, which is the Schwarzschild black hole, and I want to put it around the body. So here are our stellar black holes. They're about 1 kilometer. Intermediate mass black holes, the Milky Way black hole, which is about 1 million solar masses, the black holes in quasars, and even the universe is a black hole. So there's our universal black hole. But now let's look at some of the primordial black holes. There's the terrestrial black holes. These are the ones which are the mass of the Earth, but still about the size of a centimeter. The lunar mass black holes, somewhat smaller. The evaporating black holes, remember they've got the size of a proton, 10 to the 15 grams. The exploding ones, which are 10 to the 10th, and then the Planck mass black holes, where quantum gravity come in. And so I really love this diagram because it shows how primordial black holes exist everywhere. You know, people, even black hole people, normally focus on a particular type of black hole, that you might be a stellar black hole enthusiast or a supermassive black hole enthusiast. But, you know, I think you have to take the big picture and think of black holes in all contexts. I mean, I am a bit obsessed with black holes, as you might have understood. But the point about this diagram is the primordial black holes are the ones on the left. And they actually extend somewhat to the right. As I said, they could in principle even extend up to, say, 10 to the 5th solar masses. But the other point about this diagram, the quantum classical domain comes right at the middle, 1 centimeter. And the higher dimensional domain, which is where you're talking about black holes in colliders and things, is at the top. So you've got this nice axis of symmetry which divides the microscopic from the macroscopic domain. So that's my favorite diagram in physics. It sort of summarizes my life in a way. And I'll just, and they're the primordial black holes forming in the middle at the intersect, if you like. In some sense, the intersect of the head and the tail corresponds to the Big Bang. This is because in astronomy, when you look, if you look to a million light years, you're looking a million years in the past. And if you look to the edge of the universe, 14 billion light years, you're looking at the universe 14 billion years in the past when we were at the Big Bang. So the very large in some sense corresponds to the very small, and this is why the head meets the tail, and that's why the PBHs are forming this. The head meets the tail at the Big Bang, and that's when the primordial black holes form. So this is my favorite diagram, and I hope maybe it will be one of your favorite diagrams too. And I'll just end with the question of, actually, are most black holes primordial? Remember, we go to this diagram, we only have evidence for black holes on the right. We don't know for sure there are black holes on the left. But I would argue that if you look at the full range of primordial black holes, the only non-primordial ones are the ones between 5 and 50 solar masses. That could include the LIGO ones. Most of the black holes are in this brown region, and they would be primordial. And of course, we don't know yet primordial black holes exist, but I will only say that God will be very cruel not to populate the whole of this cosmic Ouroboros. I'm not implying that God exists any more than primordial black hole exists. Anyway, that's the end of my talk, and I want to apologize because I've taken actually almost an hour, and I thought I was going to take about 40 minutes. So Florian is going to continue now. Florian, obviously you'll be able to get to the end of the formation, but I don't know how far you can get. But apologies to Florian at least that I've run him short of time. So I'm going to stop sharing now and hand over to Florian.
Okay, thank you very much. Move to the
Let's see. Ah, yeah. That's
or
true.
the windows just plug it.
Where's it? Yeah, there. It's a bit difficult to do it afterward. Yeah. There's PowerPoint. And up. And click. Double click. And we could then somewhere when this thing disappears, there is some.
I can see it there, right?
No, it's there. Yeah, it's really over my head. It's perfect. Hello? Microphone works. Perfect. Right, do you want? Okay. Hello, everybody. So, after this great and extensive historical introduction by Bernard, who convinced you now about, did a first part, an important part in convincing you about all the different aspects of physics primordial black holes touch upon and the role they could have played. Of course, when you really want to seriously talk about them, the first thing we probably need to touch upon is their formation. And as you could probably imagine, as diverse as their mass ranges are, as diverse are the set of formation scenarios. And so by far the most discussed one in the literature, and probably the one where most people believe in currently, is probably the ones where primordial black holes form from collapse of large density perturbations, and in most scenarios they are of inflationary origin. So it's basically, I will have more slides on this, but it's basically the same type of mechanism that creates the little fluctuation in the CMB, but at a different scale and at a different amplitude, at a much smaller scale and much larger amplitude. We will learn more about this later. This is not meant to be a separate scenario, this reduction of pressure, but in the evolution of our universe and the thermal history of the universe, we have several events which we understand reasonably well, like for instance the Qcd phase transition. And during this phase transition, you have a change in the equation of state. And that causes a change in the pressure, also in the sound speed, but also in the pressure. And you have to understand, so when we are in this radiation-dominated phase, and you want to collapse a large overdensity of black holes, the pressure sort of works against you. And if you reduce the pressure, like here, it's a bit, or it's in terms of the threshold, but basically the pressure, the diagram for the pressure looks very similar. So you have the pressure on one axis, and then you have the mass or a scale. And when you reduce the pressure, you will actually lower the threshold for forming black holes, and thereby it's easier to form them. And I will show you that actually helps to enhance the abundance a lot, really, by many orders of magnitude, because there's some exponential sensitivity in most cases. Now, more exotic scenarios, I won't talk much about these. You can have cosmic strings. They may intersect and form closed loops, and under certain circumstances you can also form enough, or get large enough energy density that then forms a black hole. Similar things with phase transitions, or first order phase transitions more precisely, which go hand with nucleating bubbles, like here, and these bubbles may collide, and upon this collision, the energy densities in this collision region may be large enough to also lead to primordial black hole formation. So there's a question. So you want to?
Yeah, thanks. You might get to this later, but with the pressure reduction scenario, is the idea that it's like a local pressure reduction happening in one region, or pressure reduction all over?
I think it's all over. I mean, it's the Qcd phase transition happen. I mean, all over. I mean, in spatially in space. Yes. I mean, it's one history. So the Qcd phase transition happens around 10 to minus 5 to 10 to minus 6 seconds, depending on whom you ask, but around that time. And that is then basically all over the place. But of course, and I will show you at which places you actually get collapse of these large overdensities. So that's actually happening very rarely in space. So the probability to collapse an overdensity is which you need to form a black hole is actually very, very low. And actually, just to give you a number, I will talk about this later. Even if you populate all the dark matter with primordial black holes, say all black holes are at 10 to the 20 grams for the sake of simplicity, it's only 1 in 10 to the 15 horizon patches which need to undergo a collapse. So it's very rarely happening. So it's spatially it's rarely happening, but the pressure reduction actually is like at one instant of time, like basically everywhere. Except, okay, when the Qcd phase transition, which is still not excluded, if you, for instance, go to very large values of lepton flavor symmetries, that are indication that this could be still of first order. Then you have nucleation of bubbles, and then you have more sort of a local change of the environment. But when in terms of the most discussed scenario, when it's second order or when it's probably a crossover, then it's sort of more or less happening all over the place. Another interesting, did I answer your question?
Yes.
Very good. So another interesting possibility, which we're currently working on, a paper is hopefully out in a few weeks, is when you have quarks, don't necessarily need to be from our QCD sector, but from a dark sector, say, and they are pushed outside of the horizon by inflation. Then when they re-enter again, and collapse is possible, there's a huge amount of energy stored in the flux tube, and they would just collide, and under certain circumstances you also get black holes. Now, but probably the most important mechanism is by producing these objects from large inhomogeneities. And actually it was Bernard who derived in a simple but yet very, very nice way a mechanism when he's doing his PhD. I think the paper was from 1975, and he was just assuming a perfect fluid. So your P equal, usually you call what's now called, what here called alpha, and there was called alpha, is now W usually, the equation of state parameter, the P equal alpha rho, and in radiation you have a third, and then he was assuming, let's see what sort of, when the overdensity is collapsing against the pressure, and that was actually leading to a criterion for the necessary overdensity. So delta is delta rho over rho, so the overdensity, and this must be roughly bigger than the equation of state parameter, so roughly bigger than a third. This is opposed to, when you look for a CMB fluctuation, that you're orders of magnitude smaller, and that tells you already you need to work on the amplitude. And a big part of model building is to get the right amplitude, large amplitude at the right scale. So now, in many circumstances, people assumed a Gaussian spectrum of fluctuations. So basically, you have some diagram like this. And the primordial black hole region is those that are produced in this tail. It's more a cartoon here because it's really, usually talk about sort of like 10 sigma fluctuation. You're really like very far into the, deep into the tail. And to some approximation, you can write down the abundance. So there's a beta, which when I showed, it's a fraction of collapsed horizon patches that has an exponential form. Actually, it would be, in this picture, would be an error function, but that is basically approximated by this Gauss function. Now, and if beta is, or if epsilon is constant, so this root mean square amplitude fluctuation is constant, you can very easily derive a specific form for the Pbh mass function. And now let's go to one historic diagram, which Bernard, I guess, showed already. This is sort of constraining beta as a function of mass, different like from evaporations, and you have some entropy constraints even. And this here, density heat. Now we have, I will show you much more recent diagrams later, In this part, actually, you now have all sort of lensing constraints, but here this line is basically there showing you the saturation of all the dark matter. If all the dark matter were in primordial black holes, you would somewhere be on this line. Now, this you can translate to constraints on epsilon, so the root mean square amplitude of fluctuations. And what you immediately see here, when you, this is now in mass scale, usually you put in K scale, but the large scale structure is only basically probed down here. The amplitude is so much lower. So actually what you need, or actually before I say what you need, I say what you can use primordial black holes for. They actually a unique probe of the physics at very small scales, because CMB, as I will show you, probes a very small amount of scales. I come back to very small scales, a very small amount of scales. But these very small, much smaller scales, at scales that re-enter the horizon at much later times, they actually are not accessible by CMB and Nash structure experiments. Thereby, you either need a blue spectrum, so you need somehow to go up from this very little value, which you measure by, this time it was Kobe, now you'd probably write WMAP or Planck. But you would need a blue spectrum to increase it, to get sort of a sizable amount of primordial black holes, or you need a feature. But of course, another thing, before I come back to the question, there were some models which actually had an increase in them, but of course, you need to go down, because with primordial black holes in general, it's very easy to basically have almost zero, or too many of them, because it's very sensitive. So the art is to get the right amount, and so you need a feature. So just the blue spectrum is not enough unless you cut it off really, but you need a feature, and that was most scenarios generate that talk about primordial black hole formation. You get some. There are now many scenarios that have some feature in, say, in inflationary potential, some plateau or inflection point, for instance. There's different features, but you you need at small scales need to have sort of an increase of the amplitude. Yeah, that was the question.
Wait a second.
Yeah. So I just wanted to ask. Is there any physical motivation to assume this Gaussian distribution for the fluctuations?
A very good question. I mean, in this tail, there's, it's mainly for convenience and for us to calculate. I mean, there is absolutely no reason to assume a Gaussian spectrum in this, far out tail. So we're talking about really, 10, 20 sigma fluctuation. We're talking about really something very far out. I mean, this can be very well different than a Gaussian. This is I'm talking about the simplest scenario to show you some easy calculational results and to actually do some calculation, sure. But in fact, I will later touch upon so-called quantum diffusion, and also when you apply more refined statistical, like so-called rare event statistical analyses, it seems to be that what you get is an exponential tail. So not on the Gaussian tail, but an exponential tail. But it's a good question. We probably probe the Gaussian or something similar to a Gaussian on sort of the CMB scales for the small fluctuation. When you're going back, why is this? Yeah, if somewhere around here or so. But how the tail looks, but actually you can also reverse the argument and say, well, in order to probe the tails, primordial black holes can be very useful. That's sort of, but you're fully right. We don't have any understanding really, or any observational knowledge of that tail. So let me just again come back to the scales. So here puts the primordial power spectrum of curvature perturbations as a function of time. You measure it in number of e-folds, and here's a value you need for the CMB scale. So the CMB scales here, which probe a range of e-folds roughly till sort of below 10, say. So even the highest multiples we have access to don't really go past that line. And then now the primordial black hole scales actually are really well and way below, it's orders of magnitude below, because sometimes I get the question, probably some of you might have the same question. So how do I ensure that I do not mess around with my beloved CMB, which I we understand pretty well, we have a good understanding of, but the primordial black hole scales, if I need such a large amplitude, you see, you need to go with this power spectrum to, if you want to have, say, all of the dark matter around 10 to minus 2, and we are at 10 to minus 9 here, so why am I not in conflict? Precisely because the scales are so different. You're so much further in the past, say, and I have later on a diagram showing you when the scales really re-enter the horizon. And this is the point, but the question is how to sort of achieve this, and I will later on have some more details on the formation scenarios from inflation, say how to achieve this, say, by a plateau, which increases generically the amplitude of the fluctuations. But the CMB scales, this is I made a red box because it's for you to take home. In any case, the primordial black hole scales are really well below CMB scales. Yes, please.
Yeah, thanks. Why would that large density fluctuation show up at that one specific time?
Well, because it's there. No, because it's this is something. Sorry, my microphone. Because this is something which so far has to be engineered in some way. So this is a feature. Usually you have some models, say inflationary scenario. There's different ones, either single field or multi-field. So you have a hybrid inflation scenario, and there are certain circumstances when the potential gets really flat, you can get a large boost of the amplitude. But that is something that is very model dependent, and where exactly the peak is and how large it is depends on the inflationary scenario. I can tell you so far that you can construct it, and there are several models to do so, but the exact reason, I don't think there's a specific, I mean, there's no need for primordial black holes per se, although I think that they're very helpful for solving a lot of problems. And in the second lecture, we talk about these solving these 7 conundra, which Bernard mentioned, like providing dark matter, providing the seeds for supermassive black holes, and so forth. So far, people come up with a model, and like with many inflationary models, you have some coupling constants which you put at certain values. But eventually, I don't know of. I mean, there are models where this sort of comes out at a certain scale, but it's still one amongst several models. This is so far nature hasn't told us or hasn't convinced us that at this specific scale we need this specific feature in the inflationary potential. So yeah.
The idea is, just to make sure I got it, is that this feature in the power spectrum would come from basically the potential of your inflaton and some kind of fluctuation in that?
Yeah, so basically, let me just draw a picture here. So I think I have a picture later. But so usually when you have an inflationary potential, so let's say we have phi is here, and here's V of phi. Usually, so let me just differently. So often we discuss sort of different phases of, so I don't know whether they can see all this. So if you have an inflaton sort of rolling down, and you have a phase of slow roll, so you have slow roll, like SR, and then later on you have this phase of reheating where the thing oscillates. But actually, you can have in this evolution, and you produce some sort of CMB at some scale, and then you can have sort of an inflection point and have a potential which probably looks like this. And actually, in this potential here, wherever this is put or occurs, you will actually get an increased amplitude. So the fluctuations are much larger. And this concerns classical as well as quantum. There's a lot of this so-called quantum diffusion. Hopefully I can tell you a little bit about this. But in this, there's, there are a lot of quantum effects coming at play. But yes, right, the picture is like this. You have this sort of, if you talk about single feed inflation, there's multi-feed inflation. It doesn't need to be of inflationary origin. But if it's of inflationary origin, you're basically looking at a certain part of the potential where the field sort of, I don't want to say stuck. Actually, you need to make sure that it doesn't get stuck there. But if it sort of overshoots the plateau, then you can have a certain feature like this in the potential. This you can get. Okay. All right. So how much time do? Yeah, please. You have another question? Okay, sure. There's a clock, yeah. Well, very, very convenient.
I was just wondering, what exactly is n?
As a number of e-folds, it's time. It's a measure. It's an exponential scaling of time, or sorry, the number of e-folds. So you go with the time like e to the nt or e to the ht. I mean, you have some sort of it's a logarithmic representation of time.
Okay, and
So
then what
You
what
can
is
put scale. If you think, you can also just think about scales. You probe a certain range. Forget about time. I thought it was mentioned in Anne Green's lecture, because usually in cosmology it's a convenient concept to talk about time. But forget about time. And think just about scale. So we have a range of scales accessible by the CMB. So from the low multipoles to the higher multipoles, it probes smaller scales. And then this is telling you, from the CMB, let's say it's a pivot scale. Planck is looking at. We know that the amplitude fluctuation has a certain value, and it's relatively low. The power spectrum has to be pretty low. But then if you go to get smaller and smaller scales, those that correspond to very high multipoles, but those that we don't have really access to with the CMB. At these very low scales, you would need a feature in the potential.
okay? And then this p, is this normalized by something, or this p, the y-axis, is it what are the units, or the y-axis, this p delta or p? What are the units?
I think this is I think it's dimensionless in this.
Okay, what does it mean? Like between 10 to the minus 2, 10 to the minus 8?
I mean, it says that I mean, if you have if you look at the CMB, right, this picture here, so you have some fluctuations, right? You measure some temperature fluctuation, or which correspond to also density fluctuations. So this is a picture, a snapshot, say about like 400,000 years after the Big Bang, roughly. So and then you have you look what generates these fluctuations. Let's look at the statistic of these fluctuations. And then you can see, okay, what sort of amplitude do they have, which statistics do they obey, and the amplitude of the fluctuations, which sort of you need there, is very low, and orders of magnitude lower. And the amplitude you need for primordial black holes, because this is there's many orders of magnitude in between the size. Because looking at the CMB, actually the first pictures, I think wasn't it actually the first Nobel Prize for CMB was given about its homogeneity, and then other Nobel Prizes were given for actually its inhomogeneity. So you have different different fluctuations on like very small fluctuations, which causes in density, which causes the temperature fluctuations, and these the same kind of fluctuation that have these density fluctuations. If they are of much larger amplitude, because if fluctuations are too small, if the amplitude is too small, you would never form a black hole. You need to overcome a certain, wrote down the quantity delta. So delta is delta rho over rho, so the density contrast is called. If they're sufficiently overdense, and much more you need for the CMB, they would then collapse to a black hole. So but take it just as a sort of as a sketch. If we, I think it's probably taken quite a while to explain you all the details about this CMB fluctuation and P. But this is basically saying that at much smaller scales, the amplitude of the fluctuations, similar type than what you see in the CMB, of the same nature, need to be much larger.
Okay, thanks.
Welcome. Okay, so. By the way, how much do I have till half, or till when do I have? I mean, how much time?
Half,
okay.
because we have their lunch.
Okay, so let me then. Well, yeah. Okay, everyone is hungry, so I'm between lunch and so. Let me just where I can't click. Let me just see. Why isn't? What is happening? I can't. Yes, but well, this is actually telling you about different aspects. I can't talk about details here, but throughout the history, the value for this delta, for the critical value you need to overcome, has changed. And now numerical simulations, after going to larger values, came down to close to what Bernard was calculating. But this is now in a spherical symmetric radiation-dominated environment, you would get something like a 0.5. Of course, it depends very much on the shape, on statistics, on the specific of the environment. But actually, you would, this is about 0.45 or around a bit less than a half, if you want to remember. But one point before we go to lunch I must make is that actually, as opposed to what people were discussing before, in past literature, and still some people assume this, is a so-called horizon mass approximation. They would say, well, we have this big overdensity, this huge overdensity that somehow fits, in quotation marks, in the horizon. And when you do so, they said, well, it's pretty violent, so probably it's just almost instantaneous and having approximately the mass which is then contained in the horizon. So MH is the horizon mass, and BH is the black hole mass which you get. But actually, in the early 1990s, dated back to work by Shoptrick, it was found that the collapse is actually much more complex. So the collapse obeys so-called critical scaling. So, and that is basically the law which you get. So delta is a density contrast, so delta is delta rho over rho. And here again we have the horizon mass and some proportionality factor and some exponent. And this is not just academic sort of thought play, this is really something that has been sort of measured in quotation mark by numerics. So they were really refined simulations by Musker, Miller and Polnareff. And you can see the result here. So again, they studied a collapse in radiation domination. They looked for spherical symmetric overdensities, and then they traced it really back till horizon forms. To really, by horizon I mean a Schwarzschild horizon. So they're really sure that they have a black hole, they have a full nonlinear numerical simulation, and they put here on this axis, there's a double logarithmic plot. Here you put m over mh, the mass of the black hole over horizon mass, and here you put delta minus delta c, so what you see in here. So, and if this formula holds, you should have something, what you see actually is this line. And what is impressive, that goes down to 10 to minus 11 in this value. So it's really has been shown to hold over impressive 10 orders of magnitude. So this is really there, and this leads probably one of the last things I'm going to show you, actually to a stark difference between what you would expect by just assuming that everything is horizon mass. So even in the hypothetical situation, you say, well, I have just one scale, I put all the power at one scale, and you calculate the primordial black hole dark matter fraction as a function of mass, and I put, for the sake of fashion, everything at, say, 30 solar masses. If you assume, and you have to assume critical collapse, what happens, due to this law, well, let me just go back, so this is actually going down to quite low values of delta minus delta c, which means that black hole mass is quite low. And actually, that leads to this extended tail. So you, instead of having this peak, you get a sort of lowering, because the total amount is spread over a range of masses. And you get sort of mainly this fall of here. So and this is really important to stress, because some people still, why can't, isn't it? Yeah, but some people are still working with monochromatic mass functions and assume that this is really how it could be. But actually, with critical collapse, even if you put all the power at one scale, it's impossible to get a monochromatic mass spectrum. So it's always something which is extended. It's peaked, but still it's sort of extended. One should keep this in mind. And so probably, I don't know, we are a little bit over time. Shall I? Let me just tell you one thing, because this is something which I skipped. Let me just, wait. One thing which probably clarifies something. Inflation. Yeah, this is what I want to show you. So, in inflationary scenarios, here I put scale on this axis, and again time, Hubble. This is in e-folds again, but this is time. And this is a Hubble scale here on this plot. Yeah. And during inflation, it's constant. Then you have a phase of radiation domination, a phase of matter domination, and a phase that is describable by a cosmological constant to some degree. So, and now, what do physical scales do? So, physical scales are redshifted outside of the horizon, and at some point when the universe sort of slows down its expansion, it sort of re-enters the horizon again. And if the associated overdensity is above threshold, you would form a black hole at this time. So from this time on, you sort of probe very early, you probe the inflationary potential, if you like, if it's of inflationary origin. And also the bigger black hole, so the later you form the black hole, the bigger it will be, or you have a spectrum, but the center of the distribution would be at larger masses. And then the larger black holes probe earlier times. So in this way, if you have a sort of a mass distribution and do it properly, you could, in principle, by observing black holes, and if you're sure that's of inflationary origin, probe the inflationary potential also. And let me end with this picture, and next time I think we will continue on the formation side, on different scenarios, and also talk about quantum diffusion, and then come back to formation. So thanks for your attention.
Thank you very much. Thanks to Bernard again, who's there. And see you tomorrow then. Well, see you this afternoon and tomorrow with Florian and Bernard. Thank you.
Recording stopped.